Arratsaldeon guztioi, ohore badat, niretzat, Donostiako alkate gisa, Passion for Knowledge Quantum 13. Kongresuaren 4. jardunaldira ongi etorria ematea. Donostia kulturaren hiria da, 2016an izangoa Europako hiriburu kulturala. Eta guretzako zientzia garrantzia handia du. Beraren aldeko apostua ere egiten dugu Donostian, eta kongresu hau hemen antolatzea honen adibide garbia da. Aste honetan Donostia zientziaren hiria da. Eskerrik asko, ez naiz aspertuko, eskerrak ematen, horrela izateko lana egin duzuen guztioi. Eta Donostia ezaguna da mundu osoan, beste gauzen artean, hau bezalako kongresuak antolatzagatik. Eta ikerketan eta arlo zientifikoetan lana egiten duten Donostia International Physics Center eta Miramor Parkeko eta Euskal Herriko Unibertsitateko ikerketa eta zientzia zentroengatik ere bai. Zuek ere hemen zaudetenak eta arlo honetan lana egiten duzuen guztiak gure nortasunaren parte zarete, noski. El primer ponente de esta tarde ha mantenido una estrecha relación con la Donosti científica. Sir John Pendry ha colaborado con el Physics Center en numerosas ocasiones y está estrechamente involucrado en el proyecto del CIC de la Nanogune, el Centro Vasco para la Investigación en Nanociencia y Nanotecnología. Pendry participó en la gestación del proyecto y desde su creación en 2006 es el presidente del Comité Asesor Internacional del Nanogune. Pendry, Inglaterran jaio zen eta Imperial College London erakundeko Blackett laborategian dihardu lanean 1981 geroztik. Cambridgeko Unibertsitateko Cavendish laborategian ekin zion bere ibilbideari. Ondoren, erresuma batuko Science and Technology Facilities Council erakundeko Desbury laborategiko teoria taldea zuzendu zuen 6 urtez. Marconi enpresarekin lankidetzan hainbat metamaterial diseinatu zituen, alegia. Naturan aurkitzen ez diren propietateak dituzten material artifizial berritzaileak. Leiar perfektua egiteko proposamena izan zen proiektuaren gailurra. Izan ere, uhin luzerak ez du mugatzen leiar horren bereizmena. Sus trabajos de mayor divulgación han sido la investigación de los índices de refracción y la creación de la primera capa de invisibilidad con una aplicación práctica. Como él mismo explicaba en una entrevista, el proceso de hacer desaparecer algo es muy sencillo. Pensamos que nuestros ojos nunca nos pueden engañar y algunas veces sí que pueden hacerlo. Seguro que hoy nos explicará a qué se refiere. Su trabajo, sin embargo, no ha sido invisible para la comunidad científica y para la sociedad en general. John Pendry fue jefe del Departamento de Física del Imperial College London y decano de la Facultad de Ciencias Físicas. La larga lista de reconocimientos que ha recibido incluye, entre otros, su puesto como socio de la Royal Society desde 1984, socio honorario del Downing College de la Universidad de Cambridge, el premio Dirac de 1996, la medalla real de la Royal Society en 2006, así como la distinción con el título de Sir por los servicios prestados a la ciencia desde 2004. Y además, quiero felicitar expresamente al profesor Pendry por la medalla Isaac Newton del reconocido Institute of Physics que le ha otorgado recientemente por su valiosa contribución a la ciencia de superficies, los sistemas desordenados y la fotónica. Gaur, ikusezinaren zientziari buruz hitz egingo digu Pendry irakasleak. Elektromagnetismoak egungo teknologia modernoaren arlo askotan izan ditzakeen aplikazioei buruz. Objektu errealak ikusezin bilakatzearena, besteak beste. Please, Professor Pendry, here's your turn now. Thank you so much.
Well, thank you, Mr. Mayor, for that generous introduction. It's a pleasure to be back here in San Sebastian yet again, a city I know well, and whose scientists I've collaborated with for some years. I want to talk about light and some new technology which we have for controlling light. And to show people how powerful these new technologies are, we thought we'd do something surprising. And I think you'd agree that the most surprising thing you could do with light is to make something disappear. So we set that as the grand challenge. But I should also emphasize, although I'm going to tell you about this grand challenge of invisibility today, that in addition, the technology can do all sorts of things which perhaps aren't so exciting as invisibility, but are perhaps more important in terms of making products which you can sell, which is now beginning to happen. So let us talk about, I see my slides are in the wrong order, so sorry about this. I'll give you a backwards preview of my talk. Okay. Now I guess you can go home because you've seen the talk backwards. Yes, okay. So why are we still talking about light? One of the first things people studied when they were talking about science and how the world worked was light, because it's so very central to our being in the world. In fact, in the English language, when you say that you understand something, you very often say, I see, because seeing is believing. It's very central to what we do. And if you interfere with that process of seeing, then that's a big surprise. Now, one of the early theories of how light moves was proposed by actually two guys simultaneously. In English-speaking countries, we call it Snell's law, how light changes its direction at a surface. But in France, it's also known as Descartes' law. And I have to mention that because I won the Descartes Prize once, so homage to Descartes. If you've ever seen a ray of light strike water or glass, you'll know that it changes its direction. It refracts. And the way it refracts is described by this Snell-Descartes law. There's a quantity defined as the refractive index, which defines how much this angle changes. And this is a mathematical formula which shows that law in action. So that law, however, is based on a theory of light which regards it as a stream of particles. But it's still used because it gives a very, very physical picture of how light moves around objects. And we can see in our mind's eye how if we change the position of a surface or change the refractive index, we can immediately imagine how the light might move. And so giving people a physical picture helps their imagination. There are more precise laws, which I'll talk about in the future, which take account of the wave nature of light. They're called Maxwell's equations. And they give an exact description of light, but you mainly have to put them in a computer, except that we have now found a way of describing them that you can have them equally visual as Snell's law. So if we want a more precise description of light, because we want to look at light on a length scale that is much smaller than its wavelength, and then Snell's law is no use, we have to go to a more precise description. And the start of this story is the story of electricity and magnetism and how they were brought together. Now, one man who was very central to this story was Michael Faraday. And he had a way of thinking about the force between two magnets. When Newton spoke of forces between planets, say, in which case it would be a gravitational force, he had this picture of what we call action at a distance. So the gravitational force is proportional to the inverse of the square of the distance between two objects, and they act at a distance. But Faraday had a different way of thinking about the force. He said it happened in a two-step process, that the first magnet created what he called a field. And it was there whether or not that first magnet was exerting a force on a second magnet. And so every magnet is surrounded by this field of force. And Faraday could show this field of force, and if you've done science at school, perhaps you've done this experiment. So this is an ordinary bar magnet. You put a piece of paper over it, and you scatter some iron filings there, which of course are magnetic. So the magnet aligns these iron filings along its field lines. And this is how Faraday thought of the magnet. Its influence permeates space, whether or not it's actually exerting a force at the time. Now, the other thing Faraday did was to use this picture of lines of force to formulate his laws of induction. And Faraday discovered that there was a connection between electricity and magnetism. And if he took a coil of wire and a galvanometer, which measures the current, then if he moved the position of the bar magnet, then he saw a deflection here, indicating that change of magnetic field produces an electric current. And his quantitative formulation of that was that the induced EMF, electromotive force, was proportional to the rate at which these lines cut through the metal wire. So that was Faraday's law of induction, and it showed that electricity was connected to magnetism. So a moving magnetic field creates an electric field. Now, Faraday had no education in mathematics. He was very much a self-taught man, but a brilliant scientist, and he worked very much by intuition. But he was a great friend of another London dweller at that time, and that younger man was called James Clerk Maxwell. And it was James Clerk Maxwell who took Faraday's law one step further. So don't worry about those weird symbols. All this means is that this is how Maxwell, who was a mathematician, would write Faraday's law of inductance. And it just says that the electric field is proportional to the rate of change of the magnetic field. But what Maxwell also realized was that there was a complementary aspect to that, and that if you change the electric field, here represented by the symbol D, then the change of the electric field produced a magnetic field. And I think it was Kelvin who suggested to Maxwell that his equations should support some waves, that somehow these interacting electric and magnetic fields should produce waves. And Maxwell very quickly saw that Kelvin was right, and he produced a wave equation. And one thing that came out of that was the velocity. Now, at this stage, nobody knew what light was, what was inside light. And Maxwell showed that the velocity he calculated, which was just the ratio of the electric to the magnetic units, which you could measure, that this velocity was the velocity of light, which had been known for many years at that time. So this was a wonderful revelation, that suddenly it was discovered that light consisted of an electric and a magnetic field, and they form a dance. So the electric field changes and produces a magnetic field, which changes, which produces an electric field. And the beat of the dance is the rate of change, is what we call the frequency. And the step of the dance is the wavelength, the distance it takes for an electric field to change into a magnetic field. And so the precise picture of light is not really to be had in terms of the rays which Snell spoke of, but instead in terms of these fields which Faraday and Maxwell spoke of, because there's also an electric field just as there is a magnetic field. And this wasn't the discovery of what light wasn't the only revolution which these people produced. The other one was that the realization that these equations through electricity and magnetism produced a wave was something quite revolutionary, because at that time in the 19th century, people thought of space as something empty. If you asked the Victorian what was space, he says it's nothing, it's empty, it's the absence of things. And yet, this void, this emptiness, produces a wave. Now, every other wave which you knew was a wave in something. So, waves on the sea were water waves, waves in the air were compression of the density of the air, and so on. But light was a wave in nothing. So Faraday talked about these fields, and at this stage where it's just a static force, you could say, well, that's just one way of looking at the force, that you can either think of it produced by a field or action at a distance. But what Maxwell showed was that if you shake these lines of force, they take a life of their own. They take off into the ether. And at that time, it was postulated that actually light was in a medium, and people tried to think what this medium was. It was called the luminiferous medium, ether, the medium which bears light. Now, one man that took this story a step further was Albert Einstein, because Einstein had a picture of Maxwell above his fireplace in his study in Princeton. Maxwell was his hero and inspired his first theory of general relativity, special relativity. Now, what Einstein said was to recognize that space isn't nothingness. It is a medium, just like a piece of glass is a medium or some water is a medium, and it has properties. And one of the properties it has is something called the metric. And the metric describes how long is a piece of string in that space. Now, those of you who listened to Jocelyn Bell the other night, I think it was Monday night, or was it Tuesday? Time, of course, is compressible also. We'll know that space can be stretched or compressed in the presence of massive gravitational objects. And the way Einstein described this, or part of the way he described it, was in terms of something he called the metric. And that is just how long an object is if you view it in a gravitational field. So the metric is a way of measuring objects in space. Now, if you rewrite Maxwell's equations consistent with Einstein's theory of general relativity, what you find is that this object, which he called the metric, appears in exactly the same in the equations as the refractive index does. So as far as light is concerned, we can fake all sorts of effects in general relativity without having a black hole to do it for us. Because as far as light is concerned, if you change the refractive index, as far as light is concerned, you're actually changing the metric of space. And we're going to exploit that in designing our cloak. So with that introduction as to what electricity and magnetism and light are, let me go on to the title of my talk, which is invisibility. And the first thing I need to tell you is that it's not enough to paint something black. That's conventional stealth, which they use in fighter aircraft and bombers. And in that instance, you simply make the object black. And that's fine if you're in a darkened room and you're trying to see something by shining a torch on it, because if you shine a torch on something that's black, of course you can't see it. But that's not the environment we're in generally for light, because mostly we're surrounded by light which comes from all directions, not just from a torch which we have in our hand. And then you can see something which is perfectly black, because even though it's black, it has a shadow. And if you play the game of squash, you know that you play it with a black ball, and it's very visible, or rather its shadow is visible, simply because it's black and the surrounding court is very, very bright and white. So the real challenge in invisibility is to get rid of that shadow. And so, if the shadow goes, you have complete invisibility. By the way, some of you may recognize this figure here. It's Peter Pan. This is his statue in Kensington Gardens, which is directly opposite my college. And if you know a little bit about Peter Pan, he's the little boy who lost his shadow. So what we want to do is find a way of getting rid of the shadow. Now, those were other ways of getting rid of it, but I want quickly to come to our way of getting rid of the shadow. So this is our strategy. If there was nothing here, which is the impression we want to give, rays of light travel in a straight line through free space. So there's a straight line which would have gone straight through here. And if you want to hide something, then the light mustn't hit that object, otherwise you'd see it. So that's not seeing something, but being not in a state of not creating a shadow. You've not got to throw that light away, because you want to be able to see behind the object, otherwise you'll see a shadow instead. So the light has to be carefully guided around and carefully return to exactly the same path, stealthily. So anybody standing here will receive the same light that they would even if this object was not there. So that's the strategy. It's all very well saying that, but how do you design that cloak? And that's the challenge we've met. Well, obviously, you've got to do something which doesn't normally happen in a material. You've got to make the light go in a curve. Now, there are instances of light moving in a curve, and they occur in mirages. So this is ordinary refraction with light just changing direction from one straight line to another. But sometimes you can get a medium in which the refractive index is not a constant. It's as if you have different layers of refractive index. And that typically happens in a mirage, which if you have, for example, the hot desert floor, it will heat the air and make it less dense and less refracting near the desert surface. Further above the surface, the air is cooler, more dense, and less, and therefore more refracting. And so a ray goes through a series of, if you like, micro refractions and is bent in a curve. And if the effect is strong enough, it never hits the ground, but is turned around, and what a distant observer sees is a reflection of the sky. And your interpretation of that is the surface is wet, because wet surfaces reflect light. And here's an instance of something which appears to be wet. This is the best one I could find. This is a road mirage. So here's a hot road, and perhaps you noticed when the road's very hot in the distance, it appears to shimmer as though it's wet, even on a hot day. And when you get there, it isn't wet at all, it's just hot. And it's this effect here, appearing, and the road appears to behave like a mirror. So this is a picture taken through a long lens of that happening. And this is the effect we're going to use. We're going to change the refractive index continuously. So what I want to do is I want to create a hole in here. So I'm going to create a hole and then compress all of space here. So I imagine this is a black hole, and I've compressed space around here so that light, which would have gone straight through, as you compress, the light is displaced with the displacement of space. But where you've not messed about with space, the light is going in exactly the same direction it was before. So only in this region do you disturb the trajectory of space. And this is the technology of transformation optics, which we've developed following in the footsteps of Einstein. So that's what you want to do. Black holes aren't quite so biddable, but you don't need a black hole because as far as light is concerned, you can replace a given metric, which a black hole will create, with a refractive index. And this is how much you compress this region here. And from this formula of compression, using Einstein's formula, you can find what the metric and hence the refractive index will be in this space here. And if you can create that, then you will have a cloak. Well, the problem is how to do it. So you've got the formula, you know what you want to do, but so far you don't have the materials. And that's where these new materials come in. Let me explain what they are. These are metamaterials. Now, an ordinary material derives its properties from the way the atoms, molecules polarize when you put an electric or a magnetic field on there. And the response, the magnetic or electric response of this material, is the average over many, many millions, if not billions, of atoms. Now, the objects that you polarize don't have to be as small as atoms and molecules. They can be a bit bigger. They shouldn't be as big as the wavelength, because this averaging process doesn't happen. And the wavelength is about 0.5 micron for light waves. If you're dealing with radar waves, it's easier because radar waves have a wavelength of a few centimeters, and so for radar waves you can make metamaterials with structures which are a few millimeters across. At any rate, it is possible to make artificial structures, artificial molecules. Now, the point of doing that is that, excuse me. The point of doing that is that if you confine your ways of changing the properties of a material to changing the chemistry, you have a limited number of chemicals at your disposal. But if you introduce as well the flexibility to change the internal physical structure, then there are an infinite number of structures you can introduce. And so the range of material properties available to you is much, much greater. And I just show you a couple of things that you can do with metamaterials. So here's a structure which we wrote about some years ago. It's a series of thin, very, very thin gold wires. And the properties of these very thin wires, because they're so thin and not a solid lump of gold, it completely changes the way this material responds. So depending on the frequency, remember this is the beat of the light, depending on the frequency, the electrical response can be positive over a wide range of values, or it could be even negative. And that's rather surprising, isn't it, that you try to push the electrons one way and they perversely go in the opposite direction. But that can happen in a metamaterial. And here's another metamaterial. This one responds to a magnetic field, not an electric field. And so if you put a magnetic field down through the center of this and change its value, then that induces a current around here, which in turn, because the current's flowing in a loop, that in turn generates a magnetic response. And this particular structure has a little clip in it here, which actually makes it into a funny sort of resonant structure that also gives a negative magnetic response. And we can get a very, very wide range of responses like this. I don't have time to talk about it today, but this is one of the extraordinary things that we're that has been done with these materials. This is some work by David Smith, who's my long-term collaborator, was at UCSD then, but is now at Duke University. And he took these little copper rings and copper wires, which you can just see the shadow. Can you see? They're on the other side of the board there. So this is material in which is chosen to make a negative electrical and magnetic response. And this is the material with a negative refractive index, the first one that was ever made. You never find that effect in nature. But back to the story of cloaks. So here is what we want to do. Here's a sort of fancier picture of that. We're going to send light around. In the experiment I show you, this is going to be a cylinder with a hole cut in the middle. And the first cloak was built to operate at radar frequencies. So here's the cloak built by David Smith's laboratory. Now he's at Duke University. And you can see these little magnetic structures, which we designed in London, but David built in Duke. And the structure varies as you go from the outer ring to the inner ring. And this produces a variation in the refractive index of just the right degree to make a cloak out of this guy here. And here's a more precise view of that. So what we're going to do is to put this cloak inside a two-dimensional waveguide. So these waves move in a flat waveguide, which is about a couple of centimeters high. This is absorbing material. And radar waves are launched out of the cloak here. And this device here is to map the magnetic field surrounding that cloak. And these are the parameters which they vary with this copper ring. And as you vary these parameters, you can get various refractive indices out of this structure. So here are their data. It's a very busy slide, so let me explain what's going on. This is what happens if you use our theoretical design for the refractive index. This is a computer simulation using Maxwell's equations, and if you have the exact material properties, then the cloak does just what the theory should say. Einstein was right. Well, we knew that in the beginning, so fine. And here are the rays of light, but more important, here are the wave fronts. Light is a wave, and you can see that the waves emerge the other side of the cloak, just as if there wasn't anything there. Now, if we take the cloak away and you just have a copper cylinder there, which is the thing you're trying to hide, then the experiment shows that the copper cylinder scatters things all over the place, and in particular, there's a shadow here where you're very much able to detect that there's something in the way. Here's the simulation with the experimental parameters. This was the first cloak, so they didn't hit the design specs right on. But you can see it's doing more or less the right thing. The waves are coming out a little bit wobbly, but the wave fronts are straight. So you won't be able to see through this cloak if it were light. It isn't, it's radar waves. But what you would be seeing would be a little bit distorted, and it would look a little bit dim. And here's the experiment, and you can see that it has many features in common with the ideal cloak. So that was the first attempt and show that cloaking could be done. There were some mathematicians who said it was impossible to hide something, but they quickly backtracked and found some excuses for their theory once the experiment had emerged. And then the race was on, because people said, well, you know, this is radar waves. What we really want is to hide something from visible light. But that turns out to be harder, because the materials problem, even with the help of metamaterials, is difficult there. And so what a young postdoc of mine did, his name is Jansen Lee, and he's now at Birmingham University, was to say, let's simplify the design of the cloak. Now, there are actually three ways you can think of hiding something. And the first thing I have to tell you is another way of looking at a cloak. Now, normally when you have a lens makes something bigger. But suppose you had a lens that made something look smaller. If it made that thing look very, very small, you couldn't see it. Okay? And that's what a cloak does. It's essentially a lens which you wrap around an object, and it makes that object appear very, very small, and it's therefore invisible. Now think on a little more, and you'll realize that actually if you want to make something small, there are three ways you can do this. You can crush it to a point. So the lens, a spherical lens, crushes the object to a point. And if it's small enough, that point will be invisible. But you could make a cylindrical lens which crushed the object so it appeared to be a very, very thin wire. If it's thin enough, it's invisible. You could make another lens which crushed something to an infinitely flat sheet. And now it turns out that if we did that, that infinitely flat sheet would be a very good conductor. And so it wouldn't be invisible unless you looked at it edge on, okay. But there is, so it would be a mirror. A very flat conducting surface is a mirror, it's like silver. Where would you hide a mirror? What about putting it on another mirror? Okay, so a mirror reflects something, and I put another mirror on top of it, it still reflects something. So you don't know that there are two mirrors there. So I'm going to hide a mirror on a mirror. I'm going to make something very flat and put it on a mirror, and then you can't see it. And the point of going through this rigmarole of going from 3 to 2 to 1 dimension is that as you go from 3 to 1, 2 to 1, the cloak becomes easier to make in each case. And it turns out that carpet cloak, as we call it, it's possible to make it experimentally. So this is the way Jensen designed his cloak. There are two ways you can go about it. In this instance, all he did was to take each column of material and he compressed it in so that he created this little tunnel here. And this is sitting on a metal, which is a mirror, okay? So this cloak, designed in this way, will make this bump appear to be flat. You can also be a little clever and try to make the thing isotropic, because there are lots of choices about where you can put all this stuff which you've moved here, providing it all stays within the cloak. So what he's trying to do here is make it isotropic. Either way will work. And here's a computer simulation. And so if you have no cloak there and you make a bump in the mirror, then as you shine a beam of light over the surface, the two facets of the bump make, instead of one reflected beam of light, the two reflected beams of light. So it goes flash, flash, and you know that there's a bump there. But if you put the cloak in place here, then you always see just one beam of light coming off. Now, the real proof of the pudding is, can you make this cloak? And here is a picture of what they did in University of California, Berkeley, where they made a cloak in silicon. So here this is a two-dimensional waveguide made out of a silicon slab, so light's propagating in a plane. And they make the cloak with a variable refractive index in the simplest form of metamaterials. They just change the refractive index by drilling tiny holes in it, and the whole thing is less dense. So that's the silicon cloak, and here's an electron micrograph of it with the holes drilled. It's not a very big cloak, I have to say. This is 1 micron, which is about the wavelength of light used, and here's the cloaking region, here is the cloak. Okay, so the cloak bump are 3.8 micrometers and 400 micrometers in dimensions there. So how does this respond? Here is the theory, and here's the experiment. So obviously a flat mirror is just going to produce one beam of light. If you have a bump with no cloak, you get several beams of light from the facets of the bump. Here's the theory, here's the experiment. But if you put this silicon cloak in place, you can hide the bump, and you just get one flash of light as you shine over. So since then, people have been making progress and taken to heart the criticism that this is rather a small cloak. So here is the work of Zhuangzhang's team in Birmingham, and working with another postdoc of mine at Imperial College. They designed a cloak that could actually be made out of a naturally occurring material, calcite. And if you make this cloaked region by compressing space here, then essentially you make an anisotropic material. And if you get the parameters right, that anisotropic material is calcite. So here are prisms of calcite put in place, and they're going to refract the light so that it looks as though this inner region is flat. And so here are some ray simulations, which just tells you that it does the job. Here are some experimental data. Now, let me explain what they've done here. So this is the alphabet in reverse. And if you look at it through a mirror with a bend in it, and this is the uncloaked bump, then the alphabet will be split into two halves, so A, B, C, D, and the middle half gets scattered off somewhere else, and R, S, T, U. So this is no cloak, it's clearly a mirror with two facets. And you put the prisms in place, and you have H, I, J, K, L, and the alphabet is in the right order, and you can't see this central bump here. So that was the first cloak, which was built on a length scale of a few centimeters. This is about 15 centimeters across. So the cloak was the demonstrator for these two technologies of metamaterials and transformation optics. And our thesis was that if you could do a cloak, you could do anything. Now, since that time, some practical developments have taken place, which a few minutes I have left, I will tell you about. So there are things you can do, for example, if you want to control light, what would you like to do with it? Well, one thing you could do with it is to make a satellite communications receiver, because what you have to do there is, if you want your telephone call to reach the satellite, the aerial has to point at that satellite. And the normal way of doing this is to have a mechanical dish which you steer. It's heavy, it's expensive, it consumes a lot of power. And it turns out you can replace that with something which is about that size and is covered with a metamaterial which you can tune the properties of. So that appears like an aerial that points at this point of space or that. It doesn't actually move, it's all done with electronics. It's light, plugs into the USB port of your laptop, and it's cheap. It can be sold for about less than $1,000. And there's a company been formed, funded by Bill Gates, called Kymeta, which is about to go commercial with that project. Other things you can do is to deliver MRI signals to the body. Now, if you want a very precise image of your heart, because you've got some defect there the surgeon needs to know about, what you have to do is to get the MRI field that's going to do the imaging really into the heart. And the way they do this now is they cut your vein in your leg, they shove a copper wire up your vein till it reaches the heart, and then they send an electrical current which goes into the coil and creates the magnetic field to do the imaging. There's a problem with that. Copper wires of a meter length about resonate with the RF fields of the magnetic resonance kit. Sometimes it gets hot. When it gets hot, it sticks to the side of the vein. Not very nice. So a friend of mine in the electrical engineering department is thinking, well, why are we sending an electric field to create a magnetic field? why don't we just take the magnetic field and deliver it there? The body doesn't respond to a magnetic field except this very, very tiny MRI signal. So it's very safe. It doesn't make the body hot, and the system doesn't get hot itself. And it turns out you can use metamaterials to make a magnetic wire. So although there are these fun things, Harry Potter things, whatever, with a cloak, which are extremely challenging and surprising and hard to make, metamaterials and transformation optics are actually going on to solve practical problems which will help people in their everyday life. Now, if you would like to know a little bit more about this, I did write a popular article, and that appeared in New Scientist in January 2011, and it's part of their Instant Expert series, and I'm sure will be available either on the web or in the library. And with that, I thank you for your attention.